Hey everyone. What are we doing today? Still tired. It's the morning. Morning. But any questions on the previous lectures or homework? Today I will mention also a few things about your first lab project, which is not the actual project, but the project programming part of the assignments. So today we'll work on some of the MATLAB code, but you can use Python code, Julia code, or whatever you prefer to program in. From my perspective, MATLAB is the easiest one to learn. So if you don't have much experience with programming, you just go through MATLAB on ramp. Then a few more interactive courses that you have online for free, where they just give you some basic assignments, you type in some code, they teach you how to do that. And you can learn it practically within 1 week. All of the basics that you need to know for solving that type of problems that we will be solving in that course, because as I mentioned before, most of our problems will be probably like a few lines of code, not very sophisticated and complicated. Hopefully your project will be a little bit more sophisticated and complicated at the end of the semester, but for lab assignments, numerical methods are not too complicated to implement. All right. So previous time, just to remind you, we talked about matrices, and we talked about how you solve matrices with Gaussian elimination, which is not really Gaussian, but whatever. They call it Gaussian. And then we learned about QR methods to do that and LU decomposition method to do that. We haven't got to the actual algorithm. I just said like, well, every matrix could be written as multiplication of lower triangular matrix and upper triangular matrix, or orthogonal matrix and upper triangular matrix. And then if you can write matrix in such a way, then it would be kind of easy to solve the equations using just forward elimination or backward elimination, like we are doing always if you have single variable in your equation. So you're solving practically linear equation with one variable, and then you substitute it backwards or forwards, and then you get all of the other variables. Okay. So for triangular systems, it's very simple to solve systems of equations. So we got that place where we talked about QR and LU, and MATLAB implementation is very simple. It's just function LU and QR to get those two matrices. And the distribution for the matrix A, you just giving it matrix A, it gives you back two matrices. One of them is triangular, upper triangular, another one lower triangular, that kind. And then you can do the actual solution of the equations with triangular system, which is much easier than full system, where you do not have too many zeros in the matrix A. All right, so this is where we stopped practically. And here I want to start with the actual algorithm, how you do that, how you compute the decomposition of LU, how you actually find these two matrices, triangular matrices, L and U, and sometimes you call it L and R, like left and right matrix, triangular matrix. And this is the algorithm. So you have two different approaches to solving that system, and they're very similar. These algorithms are very similar. One of them is called Crowd's algorithm. Another is Doolittle's algorithm. And we will talk only about Doolittle's algorithm. Again, they're very similar. The only difference is that in one of the matrices, you have ones on the main diagonal. Okay, so it decomposes it into matrices. One is left, one is right. So left could be ones on the main diagonal, or right could be ones on the main diagonal. Okay, so this is the difference between the methods, like where you assign the ones on the main diagonal. Okay, this will be two triangular matrices like that. So we will do Doolittle's methods, and in that method you have one main diagonal of lower triangular matrix. Okay, so there is also additional big thing in terms of algorithm implementation of the algorithm, which is very efficient implementation of the algorithm, without using any additional memory space in the computer, which means you have matrix A, okay, which takes n by n space, right? It should be a square matrix, because only square matrices are invertible. So for that n by n matrix, you're taking n squared spaces in memory. in the computer. Now, if you develop two additional matrices like L and U, then you need space for these matrices as well, right? So you need to allocate space in memory of the computer for these two matrices, which is also n squared, each one of them. So this algorithm allows you not to do that, to skip all the steps of allocating space for new matrices and even developing new matrices. It replaces elements in the matrix A one by one in such a way that you don't need any additional space. The matrix A becomes two matrices together. And how that could work? So you know that triangular matrices have a lot of zeros, like half of the matrix zeros. In other matrix, half of the matrix is zero, plus you know the main diagonal should be one. So you can combine these two matrices together in a single matrix, like that. Like if you're looking on that matrix here, okay? You can think that this is matrix of the same size n by n, same dimensions. But all of the upper part of that matrix will be replaced with the numbers of U matrix, which is upper triangular matrix, okay? Including all the main diagonal values, whatever they are. And lower triangular matrix will be just the lower triangle of that overall matrix, okay? And since you know that for this matrix, all of these values will be one, you don't need to write them anywhere. So you just know that this is one by definition of the algorithm, okay? So practically this matrix, which is like lower part will be L matrix, upper part will be U matrix in the same matrix. The thing is that you can compute all of these values U and values L in that matrix one by one without destroying any values that you need for the computation of other values, if you're doing that step by step in the right order. Okay, so this is the smartness of that algorithm, that you can pick particular order of elements by which you are not destroying any elements that you need to keep in that matrix. So first of all, we know from that algorithm that we don't need to change the first row. Okay, so all of these elements will stay in the upper triangular matrix. So first row of A matrix will be the same row in upper triangular matrix, okay? It's not changing when you're doing the decomposition. Okay? You don't need to change it. Second thing, you can start computing from that value, which is 2, 1 value of the matrix A. And you're computing something on that value to compute lower triangular element L21. Okay? And let's see how it does it. So this is the algorithm. You don't need to pay attention to the bottom part of that. This is already solving the system of equations. But this is the LU algorithm. This 3 for loops. Okay? So let's see what it does. It takes J, which is column from 1 to n. So it says like from column 1 through n, all of the columns. For I, which is row, J plus 1. So it starts with row 2 and goes down. Okay, so it starts with this number, okay, and goes down that way. And then goes down that way, down that way, down that way, and computing all these values. So here's what it does. It takes that value, in that case, we start with 1 and 2, right? So it's like A, 1, 2. This is that value in matrix A here, okay? No, sorry, this value, 1, 2, okay? You're taking that value the other way around. So it's 2, 1, because it's IJ. So it's 2, 1. So this value, okay? And you assign it that same value recursively divided by AJJ, and J is 1, which means you're taking that value in matrix A and dividing by that value in matrix A to get that new value L21, okay? So this will be L21 computed from this value and this value. So you haven't changed anything here, right? So you touched only these two numbers to compute, okay? Now, for k equals from 2 to n, so starting with 2, you get I equals to 2, so A 2, 2, right? Equals A 2, 2 minus, which is like that value, minus A 2, 1. So what is 2, 1? 2, 1 is that value which you computed here, that value. So you computed that already, so you can use it now, and you're using it here. So this is that coefficient times A, J, K, and J in that case will be 1, and K will be 2. So it's 1, 2, that value. And since we are not changing the first row, you have it. So you're not changing it, you're not doing anything. And you compute that value now, right? And that step by step, you're going like one by one, using only values which you computed before, or values which you have not changed in matrix A. So all of them kind of fall in place to give you that iterative mechanism. And practically, if you're looking on these formulas are coming from what we learned before. This is that thing, okay? So taking the first element, you're just dividing by II value, okay, you're normalizing it. And then you're taking B minus the linear combination of other things which you computed already before. Okay, so this is the same formula practically implemented in 2 steps. This is the first step of normalization by the II thing, or JJ in that case. And the second one is you subtracting that value minus whatever the rest is, okay? And then you will get all these values. Practically, that's it. This is the algorithm. This 5 lines of thing, okay? And then you're doing forward elimination and backward elimination like you usually do in Gaussian system of equations, where you have Gaussian elimination. So you're computing these formulas as before, that formula that I showed before, okay? So you have all these formulas available. You forward with, first of all, you're doing that with one triangle, bottom triangle, and then with upper triangle, okay? So these are these 2 steps. And in homework, like right now, I will show you how to implement that kind of thing. And in your lab, you will implement the other part, the other half of the things, okay? So pay attention to the things. Here's the code, which is implementing the LU decomposition using the little methods, which is generating single matrix, which includes both lower and upper triangular matrices inside of it. That matrix that we showed in the previous slide. I'm just copying from the previous page that algorithm, and pay attention that I'm kind of following exactly the same steps. So n is the length of A, which is just first dimension of A, how many rows or columns you have. So for j equals from 1 to n, okay, this is the first row. For I equals j equals 1 through n, this is the second row. Aij, which is the element of the matrix ij, and pay attention that takes A and returns A. Okay, so you return the same matrix that you read in the first place, just modified after some modification. So you're just manipulating values of matrix A, technically. You're taking the value of Aij. This is Aij divided by Ajj, which is exactly here. Okay, same indices, same everything. And then you have 4k equals from j plus 1 through n. Aik, which is that value, equals Aik minus Aij times Ajk. So this is practically following the pseudocode or math the same way you would imagine it, okay? Index by index, I'm just copying the same thing, and in MATLAB you would get that kind of solution. So here's a simple example. You're taking that type of matrix. This is 2, 4, 2, 3, minus 2. You can take any matrix, it doesn't matter. Some rectangular, some square matrix, okay? And you're doing that algorithm, which is doing that thing. And you're returning the LU matrix. So upper triangle will be your upper triangular matrix, and lower triangle, that triangle will be your lower triangular matrix, right? So this is the correct solution, and you can even try that by hand. You have extra time to spend, okay? Do not recommend, but believe me, this is exactly what this algorithm is doing. This is how you transform from one matrix to that LU matrix. All right, and you get that type of matrix, which is exactly what you got in MATLAB. Okay, so this is just at the bottom, you have step by step how you replace the first column in the matrix, then you replace this kind of bottom triangle, then more and more you replace with different numbers. All right, you're going step by step. Any questions on that? So in the lab assignment, what you will need to do is to implement a few things. You will copy that code as is, that LU decomposition. You will add these 2 parts. So the solution will be of the system of equations AX equals to B. And you will solve it with LU. So you will not use inverse of the matrix A, which is also solving the problem, but it's not what we want. We want to solve it with LU, which is Gaussian elimination. So you will replace, you will practically implement that algorithm as it is written on the page fully to find what is X if you are given A and B. Within your algorithm, you will be using that Doolittle algorithm to compute practically triangular system, and then from triangular system you will get to solutions of X, which will be also in B. So it's very efficient implementation, which means you are giving A and B to solve system of linear equations. You don't need any additional memory to store any of the data because your X will be stored, new X, which is computed X. The solution of the system of equations will be stored in vector B that you provide in the first place. You will replace elements of B with elements of X eventually, because you see it's like B is recursively replaced with same values of B plus some add-ons. That's how you compute it. Okay, so this will be your result X eventually. So this is not B anymore after you replace values of B with computed values. And A is replaced with those two triangular matrices. You're not adding any memory. You don't need to spend any additional memory of the computer. Like you can return A and B back if you want to. All right. So you will need to solve that system of equations, and we will see particular application, how we invert matrix, how we find A inverse using that type of decompositions. So instead of going through formulas, it's complicated with determinants. And problem with determinants is that for higher order, determinants are extremely difficult and computationally expensive. And the reason is because the only solution to compute determinant is by reducing the order of determinant. If you learn linear algebra, here's how it goes. You know determinant for the 2 by 2 matrix, which is just simple formula. 3 by 3 matrix, you need to bring it to weighted sum of 2 by 2 matrices, and then computing determinants of them. Okay? They're called minors of matrix. So computing all of these minors, and you get 2 by 2 matrices from single 3 by 3 matrix, will give you 3 determinants of 2 by 2. But if you have like 4 order, you first need to get to the 3rd order combination, which is like 4 determinants of 3rd order. Each one of them will be 3 determinants of 2nd order, which eventually you can compute. But imagine your matrix is like 100 by 100. Now you need determinant of that, not determinant, inverse of 100 by 100 matrix. Okay? Like if you compute determinant of that thing, you need to go first of all to 99 by 99 matrix, and you'll have 99 determinants of that kind. And then for each one of them, you need 98 determinants of 98 by 98 matrices. And for each one of them, you need to have, until you get to order 2. To degree 2, which is like computationally super expensive. You have so many computations here recursively that you need to do that. Computers are not doing it that way. So this is the way how you actually handle it. You handle it with LU decompositions, technically. This is how you compute it. So here's the idea. Inverse of a matrix practically is defined like, let's say B is the inverse of matrix A. And we'll call it A inverse. Okay, for square matrices, is defined when AB equals BA equals I, which is identity matrix, right? So you can think about multiplication of A by B as multiplication of A by first column of B equals first column of I, and then A times second column of B equals second column of I. So you have system of systems of equations, okay? And each one of them is linear system of equations, obviously. That now we know how to solve this LU decomposition. Okay, you don't need to invert anything. So here's the idea. You're just saying, we will compute columns of B, which is columns of that A inverse, right? Because B is A inverse, like that. So you'll take A times first column of B equals first column of I, which is 1 and zeros. Very easy. So you will decompose it into N times U, right? And you'll solve it U times that thing equals that thing, okay? And then N times that multiplication vector you want to find equals to that thing. So you'll solve, again, two systems of equations, but they are linear equations, super easy and short to solve, okay? And then you will find first column of the matrix A inverse. Same thing with second column of matrix inverse. So you'll have 1 at the second place here. If you remember, I matrix looks like all ones on the main diagonal, right? So you just take in that second column, then third column, until you get to nth column. And you're solving the systems of equations, okay? So what I want you to implement in the first lab is that approach with LU, which means explicitly you're finding all of the columns and then you stack them together into A inverse. And you're actually comparing to what MATLAB says A inverse is supposed to be. And you're showing a few examples how you compute that. And it shows that this is the same thing as just A inverse in MATLAB. All right. So this is the overall idea of the lab. I will give more details, obviously, in written form, like what exactly you need to do and what are the inputs, outputs that I expect to see. All right. Any questions on that? Okay, so let's see a few applications of matrices, something more practical. So how many of you are in electrical engineering? So at least part of the class you've seen already how to solve some circuits like that, with loops, meshes, and that kind of thing, networks. And you don't really need to know any of it for that particular exercise, but it's useful to understand the motivation behind it. Typically, that type of circuits are very difficult to solve by hand, okay, if you don't know the technique. And people are doing all kind of distribution of like Y into triangle, all kind of loops, meshes, where they write all the Kirchhoff equations, or some of the voltages in the loop needs to be 0, and then you have system of equations. Then you need to manipulate the system, big system of equations. And then after a few hours of computations, you get probably wrong answer because you made some mistake on the way. Okay, this is how it works in reality. But you don't need any of it. And this is my point, that practically people just need to learn a little bit of linear algebra and inverted matrices before they get to circuit courses. Because then you don't need to think about Kirchhoff laws, you don't need to think about all the sums and loops and other things. You have just simple technique to compute all of the currents everywhere, on every resistor, through every loop, everywhere. Like everything is given just by inverting single matrix, which you write in a very technical way for any kind of thing, for any kind of circuit, planar circuit, okay? More than that, you can expand the same idea to any capacitors, inductors, any elements which produce some sort of delays, okay? Store energy in a way, all right? So this works exactly the same way. You can think just about, instead of resistors, you will think about impedances. And you know that you can replace, for example, capacitor with 1 divided by SC, which is impedance. So it will have also dependency on frequency of the input. So inputs will be obviously not DC inputs, but they will be some sort of sinusoidal inputs, let's say, okay? And then you'll be able to solve that circuit for any kind of batteries or sources, sinusoidal sources, or resistors, or capacitors, coils, whatever you have, okay? Same way, all right? And here is the idea, okay? First of all, step number 1, you drawing in each loop that you have here, like open space, you're drawing clockwise semicircle with arrow in the clockwise direction, okay? And you're calling it I1, I2, I3, I4, depends on number of loops that you have there, okay? This is step number 1. So this will be like 1, 2, and 3. 3 loops here, okay? Second step, to write matrix of resistances. And pay attention to make things more difficult. I'm using same notation for R. And in that case, R is just matrix of resistances. It has nothing to do with triangular matrices, okay? Full matrix R. This is not the same as we talked before in QR decomposition. All right, this is just R for resistance. All right, so this matrix will be n by n, and it has two different rules how to fill that matrix. One rule, you're taking all of the resistances in loop I, okay, in particular loop, summing all of them up and putting them on the main diagonal. So loop number one will have all of the resistances in loop number one. Adding them together, putting that on the main diagonal. Loop number two, you have its element 2, 2. Loop number three, element 3, 3. Okay, main diagonal, you put in sum of all of the resistances in the loop. Okay. On the non-main diagonal between I, J, where I is not equal to J, what you do, you're doing minus, which is negative, sum of all resistances which are common to I and J loops. So if they have some resistance which is like common to both loops, like for example, that resistor, okay, it's common to that loop and to that loop. So you'll put minus R4 in place 1, 2, and 2, 1. And this matrix is symmetrical, so 1, 2, and 2, 1 will be the same. Because obviously, if particular resistor is common to loops 1 and 2, it will be common also to 2 and 1, right? It must be symmetrical. So this matrix is symmetrical. It has exactly the same elements for IJ and JI. Okay, that's what it means. So this is how you build that matrix. So first step, you're making sum of all of the resistors in the loop on the main diagonal and minus sum of all resistors common to the loops IJ as every other element in the matrix. Okay, we'll see some examples soon. And then you need to write also vector of voltages. So for each loop, you will have all kind of sources, all kind of voltages in the loop. If they're going with direction of the arrow of the current loop, then you write them as plus voltage. If they go against the direction of the current, then you write them as minus voltage. And you put them in vector B for each loop. Okay, sum of all of the voltages in the loop. So it depends on the orientation of the battery in the loop. Again, we will see example. And then you can write that entire thing as matrix R times matrix I, which will include all of the unknown currents, I1, I2, I3, all of the loop currents, equals to that vector of voltages. To solve that, you just invert the matrix R multiplied by that vector, that's it. Okay. And again, we learned already how to invert that thing. And then you get vector of currents. So if you know all of the currents, clearly you can compute the currents through every resistor, all of the voltages on every resistor, everything you need to know about the circuit. Like at each point you will have the voltage. Okay, this is how you do that. So let's pick on that simple example and then try to solve it. Yes.
Is this method based on mesh currents? And
Kind of, yes.
yeah, because it looks like you need to find the loops. And the second question is, what if we cannot find the mesh loop? Because some of the circuits may like has crossover. We don't know how to.
So this is for planar circuits where you do not have kind of jump over. Like if you cannot write it, you can still do that, but the loops need to be kind of in the air above the surface, three-dimensional. You still can do that.
Still can use these methods.
Mm-hmm. Okay, so let me first copy the circuit that we'll have here. And very conveniently, number of the resistor will be equal to number of kilo for that resistor, that easy to remember. Okay, so here's the circuit. So you have battery, then you have R1, 4, 5, 2, 6, Battery will be 10 volts. Battery will be 10 volts. Okay. Else, this is. And as I said, like R2 is 2 kilo ohm, 3 kilo ohm, 5 kilo ohm, 4 kilo ohm, 6 kilo ohm, 1 kilo ohm. You need to remember, I don't need to write it, okay? Just like 1K, so on. All right. Any questions so far? This is a circuit that you want to find all of the currents in. So you'll have one of them will go I1, one will be I2, this one will be I3. You can choose any order you want, it doesn't matter really. Any order of loops. Okay. So first we write the matrix R. So what do I have here? On one element. Sum of all of the resistors in the first loop, which are, let's sort them like from smallest one to biggest one.
4 and 2.
Which one is the first one? Smallest one in the loop. 1. Do you see any 1 here? Yes. R1 plus R2 here. Else? R4. The 3 are sitting in that loop. Okay. So how about 2 element? This loop number 2.
R4,
R6.
5,
4, 5, and 6. Okay. How about the third one?
2, 3, and 5.
2, 3, and 5. Okay. How about element 2, 1, which is between these two?
R4,
Minus R4. The same thing. How about this element, which is 3, 1?
R5, R2.
Minus R2. Here we have minus R2. And the last one,
Minus
which is
R.
3, 2. Minus
Negative
R5.
R5.
Done. Okay. So if you write that in kilo ohm, it will be 1 plus 2 plus 4. It will be 7K minus 4K minus 2K minus 4K. That's 5. 15K. It's 5K. 2. 5. And the last one will be 10K, right? So what is vector V? What is the sum of voltages in the first loop? It's just 10 because it's going in the same direction. This voltage going that way, this current going same way. Plus here, okay, so it's 10. What is the overall voltage in the second loop? Zero, nothing, you don't have any data reserve. Okay, how about the third one? So this goes that way, and current goes the opposite way. That's minus 15 volts. Okay, now all you need to do is to compute I. And I will be that I1, I2, I3 will be R inverse V. That's it. So then you calculate that thing, you get some numbers. What do you get? Just practically speaking, 0.87 milliampere, 0.25 milliampere, minus 145 milliampere. Done. Practically, you can compute now any current here. So if you want, for example, current through that thing, it's I3. Would be minus 1.45 milliampere. If you want voltage on it, obviously you're multiplying current by 3 kilo ohm, you'll get 3000 times that thing. It's 3 times 1.45. The voltage of the resistor, and so on. Ohm's law. From now on, you can use Ohm's law for everything, because you have all these three currents. So this is that easy, and I probably spent like 10 minutes on that. If you know linear algebra, you don't need to take like 3 or 4 lectures on that kind of stuff. Any questions? Yes.
I wonder why R inverse is on the left side instead of on the right side.
Yeah, so first of all, I is a vector. So you have something like that. You have R times I equals V, right? So you multiply here by R inverse from the left, here R inverse on the left. Otherwise, it will not be even defined if you define it that way. You cannot I multiply by R. I is n by 1, and this is n by n, right? So if you switch the order, it will be like n by 1 multiplied by n by n. You cannot multiply I by R. Okay, so this is the only way to write it. The dimensions will not match if you switch. Okay?
Why not write V equals to IR?
Why not to write V equals IR? Because R is n by n, and this one is n by 1. You cannot multiply, this is not defined. Because this is like vector, you cannot multiply it by matrix like that. You can do technically I transpose times R, but this is something else. Then you'll have like vector times R. Technically, you can do that. I mean, you can use that kind of thing. And since this transpose is the same matrix, by the way, you'll get exactly the same solution if you're using that kind of thing. Okay, you just need to fit dimensions because R transpose equals R. Symmetrical. Okay, so you can think about that as transpose, and transpose on all of that will be backward that same thing, right? Because you switch the order of these two things when you're doing transpose on AB. Remember that rule that AB transpose, like A multiplication by B transpose equals B transpose times A transpose, switching the order. Okay, this is you'll get exactly the same thing like here. Just easier to write. Any other questions? Okay. This is one of the applications. You can solve any kind of circuits, and again, you can add capacitors and other stuff, and to use impedances instead of resistances. And let me share it again. Another very popular application of matrices, all kind of integral transforms. How many of you never heard about Fourier transform? Okay, so we have only 1, 2 people who don't know Fourier transforms. So Fourier transforms are practically the most popular tool in all kinds of disciplines, not only electrical engineering, but you have that in biomedical, you have that in all kinds of engineering, mechanical. This is how you do frequency analysis of things. So you convert any kind of time signals into frequency domain, where you see all kinds of components, sinusoidal components that combined together produce back that original signal. Okay, so you want to see like how much of a spectrum density or other things is all based on Fourier transforms. Okay, so if you don't know what that thing is, probably this application will not be very interesting to you, but technically we just convert some discrete time signal into sequence of frequency components. How strong like lower frequencies are, how strong the higher frequencies are. And if you're thinking about music, lower frequencies mean like bass tones, and higher pitch is higher frequency. Okay, higher tones is just higher frequency in that sense. So you analyzing how much of each one of them you have in the original signal, like voice, for example, voice analysis, or any other signal, by medical signals, whatever you need. Okay, and it is used everywhere in signal analysis, and not only signal analysis. Frankly, I think I looked some time ago, and like work related to Fourier analysis have more than a few 100,000 citations to the work, original work of algorithm for Fourier analysis of signals. 100,000 papers which cited the paper which introduced that into digital signal processing. Okay, and obviously you have much more than that, because not everybody is referencing the original paper. All right, so all we have is particular sequence of numbers. Okay, you can think about that as some function of time, sampled, let's say vital sign, like heart rate as a function of time. Okay, could be one of them. And you convert it into sequence of numbers, which is different sequence of numbers, which tells you how strong each frequency in that particular signal, original signal. Okay, so we'll call the original time sequence, space sequence, regular letters like lowercase letters, x, and you'll have that vector of n elements and time points, for example. And the frequency domain will be related with capital X, uppercase x's. It also will be sequence of numbers. Now you might have heard about FFT, fast Fourier transform, instead of DFT. So this is same thing practically, but not exactly. So here's the difference. FFT is algorithm name to implement DFT. So they are the same, but FFT is just name of the algorithm. It's just fast way to compute DFT. Okay? So people just came up with the idea how you can reduce some of the computations in computing the actual formula of DFT and to skip some of the steps to compute the same values. So FFT is algorithm to compute DFT. Same thing practically. Okay, same result. And here is a complicated, complex formula for computing elements. And here's why that thing somehow is related to frequencies. Remember what is exponent of something complex? Euler formula. What is exponent to j theta? That's cosine theta plus j sine theta. Okay, this is what exponent of j theta is. And here theta is a little bit more complicated. Okay, so theta here is minus 2 pi k n minus 1 divided all of these things. But you have j times something. It's some number, whatever that number is. It's just something which is sitting on the unit circle and get some amplitude of 1 and particular angle data. And that data is all of these numbers. Okay, all these variables together will give you some number. It will be your data, your angle in radian. All right. So all that thing is saying this is some combination of sine and cosine values. Okay. The real part of that is cosine, imaginary part of that is sine. This is what it is. With some weight or gain coefficient amplitude of that sine and cosine. Practically this is amplitude. Because if you multiply constant by cosine, this is amplitude, how far up and down it goes, right? Like 5 cosine something, 5 will be amplitude of that cosine, regardless of what is inside the cosine. So this is how this thing looks. And further you go, higher the frequency becomes, because this frequency is defined by the things. So higher the k is, bigger that number is. So your frequency goes higher and higher. All right, so this is definition. I'm not getting into description why this is defined that way or anything like that. If you want, you can go to DSP, Digital Signal Processing course. This is like half of the course devoted for that type of transforms. But the thing is that you can write computation of these coefficients in much simpler way using matrices. You don't need to use that kind of approach. You can just multiply by a particular matrix, which is computed from these coefficients, okay? And this will be like template matrix, like lookup table type of thing, that you compute once, and you can apply it to any signal just by multiplying by that particular matrix. And this matrix will be replicating same kind of results that FFT would do for you, okay? And FFT, by the way, is also computed matrices. This is a different story. So elements of that matrix, Kn, will be just these exponents. That's it, okay? And then if you're looking on that as this is some sort of constant, okay? Constants which are also changing. This is linear combination of values xn. Okay, you just combine xn times some number plus some other number and so on and so on. Okay, this is that sigma, n equals from 1 to n. So it's like x1 times something plus x2 times something plus x3 times something. So it's linear combination of values of x, and this is exactly what that thing would be doing for you. Okay, this is how it works. So x will be some signal vector, capital X will be frequency vector, all these elements xk, and W will be the DFT matrix, which is m by n matrix in that case. Okay, so here is simple example how it could work with Z transform and inverse transform, because all of these transforms could be from frequency domain to time domain back. In that case, it will be very simple. You just need to invert the matrix, right? So if you get from time domain to frequency domain by multiplying by matrix, then to get back, you just need to multiply both sides by inverse of that matrix, and you get back to time domain. And this will be that type of W inverse matrix. And since it has very nice structure, in particular, that thing will be kind of transpose divided by n. So here's a tricky thing that I haven't mentioned before when I talked about transpose. There is transpose for regular real matrices, where you have all of the matrices like real values, but these exponents are not real, they are imaginary, they have imaginary components, okay? So these are complex matrices. So what is transpose of complex matrix? You can think about that again as just flipping on the main diagonal and having actual transpose, but it's almost never used in practice for complex matrices, okay? You almost never want to reorganize that matrix columns versus rows, flipping rows and columns. It's not useful for almost anything in complex matrices, okay? In complex matrices, you practically 99.9% of the time using something which is called conjugate transform or Hermitian transpose, okay? People sometimes even write Hermitian with the lowercase h, which is interesting that mathematicians show that you are really famous if people start to write your name with lowercase letter. Okay, your family name. Like Gaussian, you sometimes write like with small g, not capital G. Gaussian, it's just he is famous. Same thing with Hermite. Charles Hermite is a very famous French mathematician who provided us with that type of transpose idea. And this is always like every time you will see these matrices, complex matrices, and you need to do some sort of transpose, we will be talking about that type of transpose, Hermitian transpose. And again, unfortunately, the notation is complicated and many people are using multiple different symbols to define Hermitian transpose. Some of them just write T, like regular transpose, which is not correct because this is not transpose. What you actually do, you're doing transpose and conjugate to all of the complex values. So you're replacing A plus JB by A minus JB, okay, conjugate value. Remember from complex numbers? So replacing all of these things. Or in exponents, it's like from e to the j theta, you get to e to the minus j theta when you do conjugate of that thing. So it's kind of mirroring with regard to the real axis. This is conjugate. So we always use symbol H here. Some people use star instead of H. Some people use T. And if you remember, I mentioned that for MATLAB command, you have prime. So prime always means that H. Because for real matrices, it will be just regular flipping on the main diagonal, which is regular transpose. But for complex matrices, this is what it will do. So this is a standard way to do transpose for complex matrices. And if you want actual regular transpose for complex matrices, you need to write dot prime in MATLAB. Okay? And a little bit of mess, yes.
So why is it that for real values, I mean, you just, for the transpose, in space, you just switch, but for the complex one, you have to rather use the conjugate?
It's not that you have to. The thing is that we defined orthogonal matrices, right? And for orthogonal matrices, we want that their transpose will be their inverse. This is like very convenient property. You have also unitary matrices with the same property, which have like all of the orthonormal vectors as a columns. So it's very convenient properties that we will just multiply by transpose of the matrix instead of inverse. It's very easy to compute, right? So for complex matrices, it would not work. For unitary complex matrices, that transpose, regular transpose would not work because you need to cancel out all of the imaginary parts. Like for real matrices, it does work. For complex matrices, it does not work to cancel out. And you don't want to redefine inverse as transpose conjugate. Not convenient, okay? So you define single type of transpose, which is called the Hermitian transpose, which works for both real matrices and complex matrices. Okay? And then if these matrices are unitary, orthogonal, then that kind of transpose is their inverse. Okay? So essentially, I needed maybe even in the previous slide to write, I just didn't want to define that before. The inverse of orthogonal matrix is Hermitian transpose of the matrix, both for real matrices and complex matrices. Because what I wrote before in previous slide was true only for real matrices. That transpose is practically inverse. Okay? For other orthogonal matrices, it's not true. It's just convenience kind of thing.
Can you explain the last statement you made, which is true for both real and then the
Yeah, so here's the thing. This is what we did previous time. Okay, just part. So what I defined there, I said for matrix Q, which is orthogonal matrix, okay, the definition would be that Q transpose is Q inverse, okay? So this is true if this one is real matrix, okay? But not working if it is complex matrix, right? You cannot transpose complex matrix and multiply by itself and to get back I. Because complex elements, you'll have like I squared, it will be -1, it will make a lot of mess with the real part. You know, you'll be very kind of confusing a lot of things here. So here is the correct definition. This is how it's supposed to. Okay, so Q inverse is Hermitian transpose of that matrix, and then it becomes true for any matrix. Okay, not only for real matrix, for all matrices. That's true. Okay, so this is more general than the original statement.
So the constraint is that the transpose should be equal to the inverse. Such that when you multiply it by the matrix itself, you get
So you're talking about inverse of the transform now. Inverse of the matrix or inverse of the transform, DFT transform.
So if Q is the matrix,
Q is matrix, yes.
yeah, the constraint for both the real and then the complex should be that the transpose should be the inverse, such that if you multiply the transpose by Q, you get I.
Yes. Yes. So this one, QHQ will be I. Yes. This is definition of what inverse means. Okay. So instead of transpose, you're using that type of transpose for complex matrices. Define what that is. Okay. Now, yes.
What's the requirement of the Q? It has to be orthogonal matrix.
Yes.
Still has to be.
And the reason we divide by n, like if you notice in the, let me get back to the actual slide. Pay attention that this is also divided by n. So y divided by n, and not just transpose. We said practically transpose is inverse of the same thing. So in case of that particular matrix, it's not enough just to do Hermitian transpose. You also need to normalize it by n. Why do we normalize by n? So this matrix is not really truly orthonormal. You have all these elements of exponents, and the size of the vector is not one. Okay, each column, the norm of the column in that original matrix Q is not one, so it's not satisfying the relation of unitary matrices that we talked about. Okay, they're not. It's not unitary. You need to normalize it to make it unitary. Okay, and norm of that thing will be n of each column, which means that if you divide by n, norm of each column will become one. Okay, just normalizing by n, and this is why you have the division by n to invert the matrix. Okay, otherwise it will not be correct. And here a simple chirp signal, which is going from 50 hertz to 200 hertz. You have frequencies just growing with time. Okay, it's called chirp signal. And here's how all of these coefficients x, capital X look like. Okay, these are practically frequencies in hertz of between 50 hertz to 200 hertz. As you can see, you have all kinds of numerical issues here, so it's not like rectangular wave really, because of the boundary conditions and all other like, numerical issues. But it's close enough to the rectangular window of constant frequency, constant magnitude for frequencies from 50 to 200, and nothing outside of that window, right? So this is how you analyze signals in Fourier domain. Here's simple numerical problem that you want to solve just to see that we get exactly the same thing as you get with f of t. And here are how these matrices typically look like. Okay, so this is order 4 matrix for n equals to 4, w equals, the matrix equals to that kind of thing. Okay, and inverse DFT, as you can see, is like 1 divided by 4, which is m, and same matrix but conjugate transposed. Okay, this is the idea. That this conjugate will be replacing all of the j's with minus j's, everything else will stay the same, and you doing transpose on these values, which means first row will become first column, but since all of them are symmetrical, you're not changing anything, practically speaking. So all you do is just conjugate to that thing and dividing by 4. That's simple. okay? And here, let's try some simple MATLAB example. Let's say you want Fourier transform of that vector, 1, 0, minus 1, 0. Simple 4-element vector. All you need to do to compute the DFT, you multiply by that matrix. And here I define exactly that matrix. Like you can check that all of the elements here in that matrix. Okay, just copying that as MATLAB command. And then to get capital X, I'm multiplying by that matrix from the left, that original vector X. And then I get 0, 2, 0, 2. And if you run FFT command in MATLAB on that vector, you will get these 4 numbers. Same thing. Okay, this is what FFT is doing, Fourier transform, fast Fourier transform. Okay. And you can apply that to any vector. Okay, you can start with any real or complex vector. It will work the same way. Okay, you just multiply by that constant matrix of particular dimension. Any questions? Okay, that's it for this lecture. Let's see. We still have some time. I can show you something interesting from the next lecture, maybe. So here's what we will be talking about in the next lecture. We will go to determinants and their applications, to all kinds of things like lenses, areas, volumes, and generalizations of the above. Because practically speaking, determinants are related to n-dimensional volumes. And what it even means in more than 3 dimensions, we don't really know. But we can generalize different things as we always do in linear algebra. So this is abstract thinking about what does it even mean to say length of something or distance? Like what is distance? And typically in school, you learn to measure that with ruler, with all kinds of things. But I want to show you something fun, okay, mathematically fun, which maybe will be a little bit surprising to you. And just show you that you maybe don't really understand what distance is. Okay, so here's the thing. So this is summary, we can go next time. The question becomes how you really measure distances. Okay, so you have all kinds of tools. You have lasers to measure precise distances. You have all of these wheels where you can kind of roll it on the ground and to measure number of encirclements. You have formula for the circle, so you can measure the distance. Or you have ruler, you have microscopical rulers if you want to. So you can compute particular distances using particular tools, okay? But here's the thing. I want to show you some interesting, tricky thing. What do you think? This is right triangle, okay? 90 degrees triangle. And you have length, distance from one point to another point on the main diagonal, which is hypotenuse. And I will call it A. And then I will have the other 2 sides, which I will call B and C. So what do you think? Is A the same length of B plus C, shorter, longer? How does it look like? So A clearly shorter than B plus C. Okay. Are you sure? Do you want to bet on that? Okay, let's see. I'm doing a few simple manipulations here. I'm drawing here rectangle in the middle, like middle point of the B, middle point of the C, and getting this rectangular thing, which means that AC distance is exactly as B and that corner distance, right? And C to that corner distance is exactly as AB distance. Exactly the same, like no issues at all. Agree so far? Okay, so you can draw it that way, which means B1 plus B2 plus C1 plus C2 was exactly as B plus C. Exactly, right? Correct so far? No issues, okay. I'm repeating the same process again. The sum of all of these red lines was exactly as the sum of the previous red lines, which is B plus C. I can do that many times, as many as you want. It shows that they are so different. And I can go like infinite number of times. I can get as close to line A as I want. So the distance between these two lines will be practically zero. Right? Like if I go enough steps, it's that same thing. So what is going on here? Like, are they equal? No, suddenly. I mean, in all the steps, I haven't changed the red line length. So what is going on? But now they are practically zero distance between them after 1 million steps. Have I done something wrong here? So, what does it mean?
Not perform this to unlimited, to
I'm sorry?
infinity. You cannot perform this action to infinity.
And I will get line A. So, like, what is that length thing? Okay.
It depends on how say, accurate or the number of
It's very accurate. It's like pure math.
decimals you want to measure the length. That is how we determine whether A should be equal to
So
B.
are you saying that they are different at our precision of the calculation? No, they are very different. Okay, we started with, we started with that difference. It's huge difference. Like they are very, like sum of B plus C very different from A. At least this is how I see it. Am I wrong?
So if let's say you are measuring in maybe if you want the precision to be in maybe kilometers, then they will clearly be different. But if there's
No, I measure that in
picometers,
I
that's
measure it in picometers, okay? But in picometer, like whatever precision you want. Okay, think about that, and we will talk about that next time.